All right, good morning, pre-calculus. We're looking at one last major topic. These conic section graphs are used as examples of a lot of things in calculus. Being able to do these graphs, we could spend a lot of time, if we had a bunch of time, we could spend a lot of time on geometric details of these things, but I want to get the basic idea of recognizing which kind of conic section an equation is, how to get to key points on the graph, thinking back between graph and equation for these things, and the idea of horizontal and vertical shifts. If you get how those work for functions, it's slightly different here because x and y are kind of mixed together in these. They're not graphs of functions now, but you still have horizontal and vertical shifts that are easy to pick out on some of these. And I want to work through some of the examples today. We've already done, we've done stuff with straight line graphs before and parabolas before. Sideways parabolas are a little different, and ellipses, we want to get into ellipses and a little bit hyperbolas now. So I want to work through some examples on that. If you're trying out some of these lab things from this last lab, let me know if you have questions from there that you want to go through. I will, I can do some of those. I'm going to try to do a mix of these problems so you have a chance to look at them off from this video. It's covered on the final, which is coming up here. So I guess our main announcement here is that be ready for this final exam. We got different times for these, so let me see what I got. This one is scheduled for May 6th at 3 o'clock. So it's like Wednesday afternoon at 3 o'clock. May 6th at 3 o'clock is the scheduled time for the 150 exam. I want to do 4-hour blocks for this, for the exams now, because you have to, somebody have to write these problems out, and you have to have time to get the pictures and scan them in. So I'm extending the time a little bit. So doing a 4-hour time slot, that would be 3 to 7 o'clock or so on May 6th. Now, if you have conflict with that time, if you have other stuff going on, let me know, because there's other exams I have at different times on those days, and I can fit you in with one of the others. But that's the scheduled time for the 150 exam. So I'm planning on sending them out to all of you at 3 o'clock on the 6th. Let me know if you need a different time on that. Let's work some conic section stuff today. I'll get this set up. Let's see what we're looking at. All right, so I want to work some of the conic sections that we haven't seen yet. I'm going to start with a familiar thing and kind of work out from there. So hopefully remember your distance formula and your circle formula for the graphs of a circle. And the easiest way to write this is x squared plus y squared equals r squared. I'm just going to put a number in there. So this is a circle of radius 4. Now, I'm going to mess with that one a little bit, but remember that's a circle of radius 4. If the intercepts aren't hard to find, if y is 0, this whole term is 0, and you have x equals plus or minus 4, really will work. So those are the y-intercepts of the thing at plus or minus 4 on the x-axis. And if x is 0, this term is 0, then y plus or minus 4. So this is going up to 4 and down to minus 4. That kind of gives you the basic points, and knowing this is a circle going through those points, it's not too hard to sketch in what the rest of it would look like. You could find other coordinates, but you know the basic shape of it from those key points. So we want to know along the horizontal diameter where the endpoints are, and along the vertical diameter where the endpoints are, and that tells us a lot about the circle. Let me get the shift in there. So what if we do instead, we'll keep radius 4. So still a circle of radius 4. And you know from functions, I want to tie this to what we did with shifts of functions. If you replace the x in a function with x minus 2, it moves it 2 places horizontally. It's 2 places to the right. Actually, replacing it with x minus 2 moves it 2 places to the right. That's still doing that. That's still moving it over to, in other words, instead of the center being at 0, 0 now, it's going to be moved over 2 places from there. The vertical shift looks a little different. This is happening to the y, but the y is not the output of a function anymore. It's just another variable in the equation. But this is still a +1 happening to the y. That's actually going to move it down 1 because y is -1 is what's going to make this 0. So just like the x thing, the minus moves it to the right. So it's kind of an opposite direction. Same kind of thing here. A +1 means y is -1 is where the zeros are. It moves it down 1. So it's going to move that center down 1, and we're going to be centered at -2, +2, -1. So the coordinates of the center are 2, -1 now. And it's still radius 4 around that. So coordinates are a little harder to do, but it's going to be 4 places up from there at -2, 3, and 4 places down from there at -2, 5. I keep wanting to make that a -2, and it's not. X is +2. Going up 4 and down 4 is at 2, -5, and 2, +3. And then 4 places right and left from there is x equals, now it's -2, -1. And 6, -1. That would be 4 units in all directions. So I could plot those and have good picture of where that circle is, right? Those are the key points on the circle all the way around. So if I know the center and I know sort of the radius, I can find the rest of those. So the form that this is written in we build the minuses in there, that works nicely because the h is the coordinate of it. The h and the k are the coordinates of that point, and the minus kind of gets built into it that way. So this would have a center at h, k. So you can think of it in terms of horizontal shifts, or if you write it in this form, it tells you the coordinates of the center, and then the radius is over here. That's the general form for a circle. Now, I want to rewrite that a little bit more and think about what happens with stretch and compression on here. So a different way of writing this same equation for a circle would be if I divided by the r squared to make this side equal to 1. So I'm dividing by r squared there. We don't usually do that with circles, but every term would get divided by the r squared. So that would be another way of writing this circle thing. I just want to use that as an introduction to what happens with ellipses. An ellipse is going to be very much like that. We'll still have a center at HK. But instead of having the same radius in all directions here, that was r going left and right, and that was r going up and down, we might have 2 different dimensions on that, 2 different measurements, like a bigger radius and a smaller radius. So if I go with 5 squared and 3 squared, that's a lot like a circle, but the measurements, how far it goes from the center, is different horizontally than it is vertically. So let me just put that one onto the graph without a whole lot of messing around with it if it's written in that form. So need an h and a k. If I keep that center that I had, the y +1 squared. So I'm thinking of that as y minus -1. Now k is -1, so this has a center at 2, -1. I'm going through this stuff pretty fast now. I'm hoping you've already been through some of the videos on it before and seen it, but I'm trying to pull this together with what we already know about these things. So if you're good with circles, this isn't a big difference except that instead of one radius, you could have two different radius. The center is at 2, -1 still, so on my graph, I can mark that point. That point's not on the graph, it's the center of it. The graph goes around it, but it's 5 in the x direction, right? This denominator goes with the x clearly, so it's 5 units in the x direction. From there, I can go 1, 2, 3, 4, 5. This is 2, -1. I'm going out to 7, -1, and 5 in the other direction ends up at -5, -1. Just count those off. That's my long radius on this. A major axis, they call it for an ellipse. And the 3 is on the minor axis. It happens to be smaller on this one, so it's only going up or down 3 from there. So 2, 2. Or 2, -4, counting up or down 3 on the y-axis. And the shape is a lot like a circle, except it's flattened out some, right? It's narrow. 3 in this direction and 5 in this direction. So it's a stretched out circle. And that is the stretch or compression stuff happens when x is multiplied or divided by something. It's set up as a division in this equation, but that will stretch or compress it differently for x and y. And the easiest thing is to write it in this form. And then you know what both of the radius values are, and you can go to the graph from it. Now, the fact is they don't always start off with this form. So let me think this thing through as a sort of polynomial problem and see what the issue is. If these are written out algebraically, we may have to switch back and forth between these forms. So this, if I was just an algebra student and I'm looking at x minus 2 squared over 5 squared and y plus 1 squared over 3 squared equals 1. If I just do the algebra sort of simplifying on that, I got a denominator on that. I got parentheses I can get rid of. So if I didn't know better, I would want to get rid of the parentheses. I'd want to get rid of denominators. I might multiply by something to get rid of the denominators here. Common multiple of these would be, what's 25 times 9? 225. So I might multiply everything by 225 to get rid of the fractions. Doing what my algebra instincts tell me to do on this. Get rid of the denominators. I got 9x squared minus 36x plus 36 plus 25y squared plus 50y plus 25 equals 225. And I got some like terms now. I don't have a lot of like terms. I got x squared and x term, y squared and y term. All of the numbers are kind of like terms. So I might put all those together and it might look like this. Algebraically, as strictly a polynomial, this is the kind of thing that I'm looking at. 164 with the terms put together. But I can still tell, even though that's not set up nicely for graphing, I can still tell in that form that it is an ellipse. The existence of both of these terms with two different numbers but the same sign there. They're both positive, the 9 and the 25. So I have an x squared term and I have a y squared term with different coefficients with them, but the same sign. That's always going to turn into an ellipse. Then I can push it around into this form and have an ellipse equation. If they had the exact same number on both of them, then it would turn into a circle because my two radius things would be the same. So it would be a circle If you have the same number, it's a circle. If you have opposite signs there, it's going to turn into a hyperbola. Those are the ones we're going to introduce a little bit, but we're not spending a ton of time on hyperbolas. That's a little harder. I want to draw a picture for that. So if I start off with an equation that has those things, then I know it's going to end up as an ellipse. If I need to get the particulars for the graph, then I got to push it into that nice graph form where I have the perfect squares. So that involves, if you think about reversing these steps, it involves some factoring and some completing the square stuff in there. That can be a little challenging to do. Again, we're trying to get the basics of this, but let me start with a fairly nice one and work through going in that direction. And take one out of the book so that I know it'll probably come out fairly nice. So here's what the line look like. This actually one I have marked, I think, was part of the homework. So if you tried number 50 from here, it's the ellipse problem, where it starts off with just a whole bunch of terms. And they're in this order, but I'm going to rearrange them a little bit. I'm going to need to. But I have x squared and y squared terms. All right, let me do a little sorting while I'm on the topic right now, both of those terms. So here's the rundown on these things. If I have an x squared term and no y squared term in it, then that's graphs like y equals x squared, or you got a y term but no y squared term, you got a parabola. We kind of know a little bit about those already. Upward or downward parabola situation. If I have comparable to that, if I have a y squared term and no x squared term, well, that's an x equals y squared kind of thing. It's a sideways parabola. Maybe it goes either direction, but that's a sideways parabola. Opening to the left or the right. I do a quick summary on these things. If I have both x squared and y squared terms, they're both in there. They have the same number with them. It's a circle. If they have different numbers, same sign, that's the kind of thing we're working on now. That's the ellipses. Different coefficient number, but same sign on your x squared and y squared terms. Different number, same sign, then it's an ellipse. You'll have two different sort of radius things. And if you have an x squared and a y squared term with opposite signs, when they're on the same side of the equation, but they have opposite signs, one of them's positive, one of them's negative, then it's going to be a hyperbola. And that's really all of the possibilities. If you have both of those terms, then one of these things has to be true about the numbers. You're in one of these categories. One of the squared terms, then you have this kind of parabola, this kind of parabola. And if you don't have any squared terms at all, then you have a straight line equation. Just x and y terms, where it's just straight. So that kind of covers all the possibilities. So this one, if we just look at it, we can tell right away they're both positive, but two different numbers. So we're talking about an ellipse. We know it's going to end up as an ellipse. Finding points on this would be kind of inconvenient by plugging numbers in. So instead, we're going to try to write it in this nice form. We're going to shoot for this form. It's going to be a plus because the squared terms are the same. So that makes the plus there. But we'll have some denominators there, and we're trying to get it equal to 1 on this side. So the first thing I want to do is get my x and y terms sorted out. I'm going to have to work through the sort of backwards steps of getting it into this form. So I want to get my x squared and just y. Do the factoring right away. The 5 yet. leaving a little extra space because I got to do my complete square stuff. So if you're one of those people for whom complete square was never your favorite thing, well, you kind of need her. This is one of the places where you're using it. Quadratic formula isn't going to help you here because you're not trying to solve for x or y in this. We're trying to get it written in perfect square form, so we kind of have to do that. But divide by 2 and square it thing, right? 2 divided by 2 is 1. Squared is plus 1. And I have to think about what I'm doing right here. If I put a plus 1 inside there that wasn't there already, I'm really adding 4 to this side of the equation because I'm adding 1 inside the parentheses that are multiplied by 4. So that's really a plus 4 on that side of the equation. So that balances out what happened there. And then, same thing here. There's a comparable thing here. This was a minus 2y. Half of that is negative 1 squared is positive 1. So I'm going to throw in the plus 1 here also. Times 3, that's really adding 3 to that side of the equation. So I'm also adding 3 to the other side of the equation. That is typical with these. We need to make the perfect squares show up. So we need to add or completing the square term in there. See how that affects the other side of the equation. Now, here's what I got is the in-between stuff. So far, I've got 4 times this perfect square. I'm going to go ahead and write it in perfect square form. 3 times this perfect square, that's y minus 1 squared, equals, and 9, 10, 11, 12. I got 12 over here now. I need to have 1, so I'm going to divide by 12. Whatever number you end up with, you can divide by it everywhere, and you'll have something that simplifies a little bit. Well, the numbers come out nice on this one. 4 over 12 is 1 over 3, so this is, you know, it's 3 in the denominator. It's x plus 1 squared over 3. And this is 3 over 12 or 1/4. So this is y minus 1 squared over 4. And I got my 1, and now I'm in that perfect square form, but be careful with the numbers here. Those squareds are there. So this is centered. HK is this coordinates of the center. This is minus 1 and this is plus 1. Remember the minuses in there. This is y minus 1, so k is 1. This I have to think of as x minus negative 1 because h is negative 1. That's the horizontal shift to the left on that. So I'm centered at negative 1, 1. You sort of have an x radius and a y radius that you want to know for the graph. They call them A and B in a book. So but this is squared, right? 4 is 2 squared, so the y radius is 2. 3 is this thing squared, so the x radius is really square root of 3. Careful, it's got to be square root of 3 squared to be equal to this. 2 works here. Square root of 3 works for the others. So this is the B and the A. I don't know, make a big deal about what letter is which, but for ellipses, we want A to be the bigger of the numbers. And it ends up being in the y direction. This is going to be bigger in the y direction and a little narrower in the x direction. We can tell that. So we can go to the graph from that. This was a pretty rough one that had all the terms in there. This is the process you have to go through with the numbers and see what you end up with here. But if they started off with the same sign, they're going to end up with the same sign here. And you got all the information you need to sketch the graph. Now, negative 1, 1 is the center of the thing. And we go up or down 2 from there to get to the graph. Negative 1, 3 is a point on it. Negative 1 is a point on it. Graph is coming through these. And then the x direction is just square root of 3, which is less than 2. So 1y is 1. X is negative 1 plus square root of 3. comes out small positive right there. And -1 minus square root of 3, comma 1 is the other point on the other side. Crowded graph right there, but you have the information that you need to put on the graph. The A ended up being our Y radius, and the square root of 3, the B value, ended up being the X radius. And when you get in that final form, you can tell which one's bigger, and you know basic kind of shape that's going to have. Now, if these are centered at the origin, then there's a lot less work to them. The H and K are 0, so you don't have the whole completing the square thing. That's a lot nicer if they're just centered at the origin to do some of those, but you should see some of the difference on that also. I'm not going into foci and all of that. There's geometric details to it, but not going through all of it. That's what you need for the graph. You can think of this whole thing as living within a box. It does live within a rectangle. Where if you know the center and you know your A and B values that go in either direction, you can mark these points, and this whole triangle lives within, or this whole ellipse lives within that nice rectangle right there. That is all based on what numbers you have here for H and K and what numbers you have here for A and B. That rectangle is the key also to understanding how hyperbola graphs work. I want to get through one of those. It's just kind of quick summary. We're going to stay centered at the origin on the hyperbola and just do one that's centered at the origin. But that's when we have x squared and y squared terms with opposite signs. We're going to have to work through one of those. Let me start with a fairly nice one. It's actually 10.4, number 31. I am taking these from the book, so I'll write that down. So, I don't think is on the homework. But 10.4, number 31, this is 4x squared minus y squared equals 16. I don't have x and y terms on it. And for these kind of things, that means it's centered at the origin. The x and y terms are the things that end up being the turn it into the H and K, turn it into the coordinates of the center. If they're both 0, then this is centered at the origin. So I already know this is centered at origin. And opposite signs here, this is 4 and -1, right? So they're opposite signs, so it's a hyperbola. We got to talk about what that means. A lot of the form is the same for a hyperbola. We're still going to try to get our perfect squares here, which is easy on this one, but we're going to have opposite signs on them. So when we get this equal to 1, we're going to have something that looks like this, but it's got to end up equal to 1. I'm guessing a little bit that this is going to end up the positive 1, because if my y stuff is over here and my x stuff is over there, I got to see which one ends up positive. But here we go with that. For this one, h and k are 0, so I know that's just x squared and y squared. I need to get the 1 and see which one ends up, what numbers I end up with here, and which one ends up positive. But sure enough, these are kind of nice perfect squares. I'm just going to divide by the 16 to get the 1. I'm already ready to do that because I don't have any completing the square to do. This is x squared over 4 minus y squared over 16 equals 1. And we're in this form. The h and k are 0, which I knew. And a is 2. A squared is 4, so a is 2. That's the direction in the x direction. That's how far it goes in the x direction of the box. And b is 4. B squared is 16. B is plus or minus 4 in the y direction. That's where I'm going to go in the y direction to get box. This is not an ellipse, but I'm still going to draw this rectangle and see how this thing goes from here. Centered at 0, 0 this time. 2 is, A is actually smaller than B in this, but A is whichever one's on the positive term here. In this case, A would be X. It's 2 in the X direction. So I'm going 2 units in the X direction to 2, 0, and negative 2, 0. And I'm going 4 units in the Y direction up to 0, 4, and down to 0, negative 4. Those are the points in the rectangle. I can still draw this rectangle, but then it's going to look a little different from there. So 2 this way, 4 this way. There's the rectangle that this lives around. Now these points are not all actually on the graph. If I plug in 2 or negative 2 for X, it ends up 1 minus 0 equals 1. These check out as being on the graph. These, if I plug in 4 or minus 4 for Y, I get negative 1 right here, 0 minus 1. It doesn't come out on the graph. These are not actually points on the graph, and these are. So for this one, you have, they call it transverse axis that actually hits the graph, and you have a conjugate axis that doesn't actually hit the graph. These are the only points on the graph of it. And what it does from here is actually follows out the diagonals of this. So if you can draw in the little box, you can draw in some diagonals that go this way and this way. The graph is going to stay outside the box from these points that are on it and just follow these diagonal asymptotes. So that's what the graph for this one looks like, diagonal. Asymptotes. Your A and B in this determine where the box is, and then you can draw in the diagonals, and this thing is going to approach those diagonals and stay outside of the box. So it sort of turns what would have been an ellipse, sort of flips it inside out, folds it inside out to following outside the box, like this. So the fact that the X term ended up the positive one, that means it's this way. The ones on the X-axis are on the graph. And if we had one where the Y term is the one, the Y squared term is the one that ended up positive, then it would be staying outside the box in the Y direction. So you have to be careful about which way it goes based on the signs up in there. There's a few different possibilities on that. That's a brief introduction to these things. I'm glad you have some other videos to watch on this, but I'm going to do I'm going to go to the end of chapter 10, the review. So we're not doing all the details on chapter 10, but I'm going to do one of these where you don't know which type of thing it is from the start, and you got to figure it out. Can I find out? Let's see stuff. Identify each equation, if it's a parabola, if it's an ellipse, if it's a hyperbola. So we want to be able to look at these and then work them through if we need to find the graph. So if you look page 699, review exercises 1 through 10 here. You want to identify which kind of conic section we're looking at. Number 7, I'm going to work through and do, but I want to look at a few of these just to identify what we're looking at, what is going on with these things. Number 1 is y squared equals minus 16x. I just want to identify that's a parabola because I don't have an x squared term. I have an x term and no x squared term. This is just like a stretched version of x equals y squared. Right? So this is a parabola, sideways parabola. I don't know which direction, but horizontal parabola. Number 4, x squared plus 4y equals 4. Again, well, in this one, there's no y squared term. So this is just like a y equals x squared thing. This is a vertical parabola. You can solve for y in that thing and get a simple parabola there. So vertical parabola. Number 7, y squared minus 4y minus 4x squared plus 8x equals 4. This has kind of got all of this stuff in it. It's got an x squared and a y squared term in it. They're opposite signs. So I know it's going to be some kind of hyperbola. And I have to work it through into the nice equals 1 form to see which is the positive term, whether it's a sideways hyperbola or an up and down hyperbola. I have to see as I go along on this. So it's a good idea on these things to write down the form that you're looking for or trying to end up with. But I don't really know to start with which one's the x and which one's the y in this, because I got to see which ends up positive. Looks like the y is going to be positive in this one. But let's do that. I got to do some completing the square stuff, because I do have x and y terms. I got to figure out where that h and k are. So sort it out. Here's my y stuff. Here's my x stuff. Here's my number. Factor. Well, I don't have any factoring here. This is y squared minus 4y. It's going to be plus something. I have a negative 4. I have to factor out of this one. Negative 8 divided by negative 4 is negative 2. Sorry, positive 8 divided by negative 4 is negative 2. I'm going to have to add some stuff to both sides now on this one. But I do have a minus. It is going to be on the x thing. I got to see what the numbers are. So completing the square on the y, negative 4 divided by 2 is negative 2. That's my k is 2. Squared is plus 4. When I add a 4 there, I'm really adding 4 to that side of the equation, so I got to add 4 to the other side. And on this one, negative 2 divided by 2 is negative 1. Squared is plus 1. When I throw a plus 1 in there, I'm really adding a negative 4 to that side of the equation. That's a negative 4, so minus 4. Here's what I got so far. Y minus 2 squared minus 4 times x minus 1 squared equals 4 plus 4 minus 4 is just 4. Now I got to turn that into 1, so I'm dividing by positive 4. 4 divided by 4 is 1. So that's the nice form of this thing for graphing. H and K, you hear this is centered at 1, 2. Plus or minus 1 in the x direction. That's the sort of B here. I'm going to go either 1 unit in the left to the left or right. And a squared is 4. So a is 2. I'm going to go plus or minus 2 in the y direction from here. So put all that together on the graph. Now I get a little space. 1, 2. This is a pretty hefty problem. Center is at 1, 2. I got all this stuff going on. 1 unit in the x direction from there. And 2 units in the y direction from there. It's going to go up to like 1, 4. And it's a narrow little thing because it's only 1 this way, but it's 2 this way. That's the graph. That's not the graph. That's the box. The graph is going to stay outside of the box and follow these diagonals because it's a hyperbola. It's a minus. So draw your diagonals to this thing, and diagonals go through the center and the corners. And then think about which one is really on there. Since the y squared was the positive term, this is really going through the points in the y direction. These are the actual points on there, what they call the vertices of this thing. They're really right here. That's 1, 0. When y is 0, you get 1 here. X is 1. You get 1 minus 0 equals 1. This actually works on the graph. And so does 1, 4. Those are the points actually on the graph. So it's a vertical hyperbola following those diagonal asymptotes. Turning this into kind of a long video, I want to get some of these examples in. Hyperbolas, there's the most going on because you really have to draw the box and the diagonals and all that. There's a lot more going on there. That's a pretty thorough example on that. I'll do one of the others here. Recognizing these things is kind of nice. When you're going through calculus, you're really not expected to know everything about conic sections, but if you can see one of these kind of equations and recognize which kind it is, that really gives you an advantage when you're doing graphing stuff or thinking about these in calculus. So I really like to do that. Numbers 2 and 5 have to be hyperbolas because they have the x squared and the y squared with opposite terms. I'm going to do another ellipse problem. I'll do number 3 right here because it's really mostly set up for us. They don't always start with a whole bunch of terms all over the place. This one's pretty much in the shape that we want to do. But it's got x squared and y squared terms. Both positive here, same sign, different numbers. Coefficients are 1 over 25 and 1 over 60. It's already written with the equals 1 in there. But there's x squared and y squared terms with the same sign, different numbers, so it's an ellipse. It doesn't have x and y terms, so the h and k are already 0. We could write this as minus 0 and y minus 0. Right? We're not moving the center from the origin, so centered at 0, 0. (25) and 16. This ended up being the bigger one with the y, so a is 5 in the y direction, and b is 4, a nice perfect square again, in the x direction. You have to get numbers down here. They don't have to be nice perfect squares, but here they are. So a and b end up being nice simple numbers. That's good for this one. So the graph of that, I can draw the box, but the ellipse stays inside the graph. Centered at 0, 0. 5 units in the y direction, plus or minus 5 in the y direction from here. That's 0, 5, 0, negative 5. 4 units in the x direction, 4, 0, negative 4, 0. You can draw the box if you want to. The ellipse stays inside of it and actually hits all 4 of these points. With the plus right there, we get all 4 of these points are on the graph. So your actual graph is just the ellipse. Almost circular in this one because it's almost the same. Major axis and minor axis are almost the same length there. That's what we've got for an ellipse on them. Let me go back and spend a little more time on parabolas because I've been sort of brushing past the parabolas, and we haven't really worked with sideways parabolas a little bit. So sideways parabola is one that has a y squared and no x squared term. That was the situation that gave us a horizontal parabola. By that I mean this kind of shape that opens to one side or the other. So I want to do one of those. So I'm looking at one that has a y squared and no x squared term. Do we have one in this exercise set? Let me go back to the parabola section. In the chapter, they're all sorted out by which type, and then in that chapter review, they're mixed in together. So I'm going to go back to just parabolas. 10.2 was all the parabola stuff. Equation might start off like this. Here's one, number 49. This is y squared minus 4y plus 4x plus 4 equals 0. So these are good. There's going to be a few of these on a couple of these conic section problems. They're good practice. The homework's going to count as a, what did I say on it? I think it's going to count as a bonus homework for these things. So if you turn these homeworks in, it'll just be extra bonus points that'll be added to your homework average. Homework averages are already pretty good for most of you. But these are good practice to do. 49 is one of them. Just to get this sketch of this thing, it says find the vertex, focus, and directrix of each parabola. I'm not going to stop and worry about focus and directrix now, but we want to be able to graph this thing, and the vertex is the key point on these things. Of course, we want to know where that is. That's your HK for these things. I want to actually get the squared term by itself, or the perfect square piece by itself. In this one, it's y squared. Well, it's going to be y minus something squared, but I want to get the y stuff on by itself on one side of the equation. So moving everything else to the other side to start with. And then do the completing the square on this. This is going to be y minus k squared. There's no x squared, but that means k has to be -2. -4 divided by 2 is -2. -2 squared is 4. So I need to add 4 to both sides to make that the perfect square. So that's my plus 4 on both sides. Didn't have anything factored out on this one. That's nice. And that ends up just -4x. So that ends up with a number and an x term on that side. I can write it that way. I didn't end up with a number because that came out to 0. That's really the coordinates of the center. Then is when y is 2 and x is 0. So that's 0, 2 is the vertex of this thing. So on the graph, start at 0, 2. It's not going up or down in this. It's a y squared. It's going to the side on this. The minus out here means it's opening to the left. If you stop and think about your domain and range for this deal, well, this has to be positive. The squared side is always positive. So in order for this to come out positive, x has to be less than or equal to 0. That's what we need here. Everything is to the left of the vertex on that. So it's opening to the left with this negative sign. That'll open to the left. We get points over there. That's where the vertex is, and it's going in that direction. That tells you a good sense of, it gives you a good sense of where that graph is going. Not going to dig into all the details on that about the geometric stuff with it, but that gives you a sense of what that graph looks like and the key point on there. You could sort of solve for y in those things. If you do your square root property here, you'd have a plus or minus on it. Y minus 2 equals plus or minus this. You could actually get some stuff to go to the calculator on these. The top and bottom are functions, but you'd have to do a plus or minus on it because one function would be the top half of the parabola, and the other function would be the bottom half of the parabola. We can graph it all at once using what we know about parabolas, but if you wanted to put this in a calculator, you use your square root property. Y minus 2 squared equals -4x. So y minus 2 is plus or minus the square root of 4x. Square root of x if you want to simplify it down. So y is 2 plus or minus 2 square root of x. That's starting at 2 I'm sorry, that minus got lost in there. That was minus 4x. That's inside there and has to stay on the x. So x has to be negative, and you got 2 plus the square root function and 2 minus the square root function. These could actually be done in the calculator. Conic sections calculators aren't great for these because most of them are not a simple function of x. Most of them are. If they fail the vertical line test, like I said in the announcement up there. But this one could be done. Two pieces. 2 plus 2 square root of negative x and 2 minus 2 square root of negative x. Graph on that. Yeah, that's the graph we ended up with on it. So it is two separate things, that the plus and the minus. You can kind of see them graphing separately on there. That's the top half and the bottom half are both functions of x, and you can put them in that form, parabolas. All right, so that's just part of the final. We're not taking a separate test on conic sections. It's just going to be a few of the questions on the final. So get some experience with that. Turn in what you do on that, and I'll count the points as extra bonus points on that. And then we have time on that because final exams later in next week, so you can turn those in anytime. Get some practice on the earlier stuff. Also, look back through your old tests, see what you understand and don't understand from that. Just getting prepared for the final. I'll try to get some review questions up a little later. We got a little time on that, so I will have an announcement Monday going out, like I have been, just with some review stuff for the final. And just get questions to me anytime. I'll try to get back to people if you have questions. So if you're going back through old tests or practicing in Lumen or whatever, you run into something you don't remember or you get stuck on, let me know. I'll try to keep people moving on that. I'll try to get some review stuff up soon. This conic section stuff, you have a little time, you can turn it in whenever. And looking at the final, let me know again if that time isn't good. We're looking at late afternoon on May 6th there. If that works for you, great. If not, we'll find something else. So let me know. All right.